about data link, right? When we talked about data link, um, so we talked about data link in the context of ensuring that the frames that are sent, right, are basically received correctly, right? So you need to detect whether there is any kind of error that goes on, right? So that is one thing. And second thing is that if there is any problem that goes in, you also need to ensure that appropriate levels of correction can be can be had, right, in these links. So data link, whenever we talk about data link, one part is the control. So the control, basically data link control, which we covered previously, can have broadly two important components. One is basically this error control that I just mentioned. The other one is to ensure that the receiver is not overwhelmed by the sender. So that is basically called the frame, error control and flow control. It is called the flow control. Okay, so flow. So ensuring that the receiver is not overwhelmed by the sender. Okay, that is basically ensured by the flow control. So those are basically two very important components of data link control, right? These are very important components of the data link control. However, even if you are using, so for example, for flow control or error control mechanisms like stop and wait, or mechanisms like sliding window, etc., and there are different other variants that I that we went through, like selective reject is one improved variant for use in data link control. So like this, actually there are go back in selective reject, etc. So many of these different mechanisms that we went through in a previous class on data link control, these are important, but these also have certain limitations, right? These basically can only ensure what they are supposed to do. That means whether there is any kind of flow mismatch between the sender and the receiver, or whether there is any kind of error that has gone in. So it can do only this much. But there is another very important component that is very important, particularly when we are talking about not just two stations, but we are talking about multiple stations sharing a common medium, right? So we have, let us say, a wireless medium, the ear interface, and through the ear interface, we have multiple stations. That means multiple computers, let us say, which want to transmit data between each other. Okay, so how this can be done? So for this, for this basically, we need to take help of mechanisms called medium access control, which is part of multiple access protocols, right? So medium access control. So for this, basically there are different protocols that are in place, and we are going to cover those. So as you can see over here, in the next class, basically we are going to talk about the different layers, which I have been promising you since the very beginning. So data link layer, which is basically also called the layer 2, so don't be worried once again about these different layer names and their numbers. So for now, just focus on this thing, that data link layer has two main components. One is basically the data link control, like flow control, error control, etc. And the other part is basically this medium access control, which is basically achieved through some very important protocols. Is this clear? Any question? Okay, so these are the main functionalities of the data link layer. Now we'll come back to again the functionalities of the different layers in the later class, but for now, just so it is sufficient to know that these are the main functionalities. So whenever we are talking about this medium access part, right? So where there are multiple stations, common medium, shared medium, how these stations they are going to how they are going to communicate with each other, right? So the issue that comes into mind is that if you have such a scenario where there is a shared medium, whether it is wireless or wired, and you have multiple stations, the thing is that who sends the data that they hold at what time? Because if everybody or more than one station tries to send data or the frames at the same time, then obviously there will be some collision in somewhere in that space, right? Whether it is the wired or the wireless, somewhere in the space there is going to be some collision, right? Because multiple stations trying to send data at the same time, there is going to be some collision. So due to this collision, what is going to happen? Due to this collision, the consequence is going to be that either the data is going to be completely, the frame is going to be completely lost, right? It is going to be completely damaged. The frames are going to be completely damaged, or some bits are going to be altered. So every frame has certain number of bits. So those bits are going to be altered, or the complete frame is going to be damaged. So you see that collision is not desirable, and that is why you need to discipline these different stations so that not all of them try to send the data at the same time. It is something like this, that in the class today, right, we have a shared medium, a shared platform. So we have this Teams platform. Now imagine that multiple students, they ask different questions at the same time. So will it be possible for me to understand the individual questions? It is not going to be, because so everything is going to be all the different things that the different students they talk about, they are all going to be mixed up, they are going to be jumbled up, right? So the data, basically the signals that are coming from the different students, they are going to be basically altered, right? They are going to be altered. So either completely it will not be understandable, or partly it will be understandable, partly it will not be. So in the same way as we need to discipline over here, that which student speaks when, if they have certain questions to ask, right? In the computer networks also, whenever you have multiple stations or multiple computers which are basically which are talking to one another through a shared medium, right? So how they are going to be disciplined, right? So for this, who talks when, we have to come up with certain mechanism, right? So for this, basically, there are three main classes of protocols that have been proposed. Okay, three main classes of multiple access protocols. Number one is called random access protocol. Number one is called random access protocol. Number two is called controlled access protocols, and number three is called channelization protocols. For this particular course, our focus will be primarily on these random access protocols, and also to some extent on these channelization protocols, and minimally on the controlled access protocols. So random access protocols are the most important for us. Okay, so these random access protocols, there are a few which are very popular. One is called the Aloha, second is called the CSMA, third is called the CSMA CD, and the fourth is called the CSMA CA.
Sir,
So
we cannot see the
likewise,
slide side.
oh, is it? Oh, you should have told me. Okay, very sorry about it. And I hope, yeah, you see that this recording also, it is the previous one is continuing, but let it continue, because if we stop now, then we have already covered some part of it. Let it continue. So basically, two lectures in one recording is going to be there. So let me unshare the previous one and share this one. Yeah. Okay, so thanks for pointing out. Is it now visible?
Yes, sir.
Okay. So we were talking about this, right? So we were talking about this taxonomical classification of these multiple access protocols, random access protocols, controlled access protocols, channelization protocols. So random access protocols, these are the very popular ones. So make sure that you understand these very well. I'm going to cover very shortly. I'm going to in fact cover all of them, right? So so we have little time left. But the way I will cover, if you listen to me very carefully, so you will know these very well. Like even if these are quite time taken to understand, but if you listen to me very carefully, half of your preparation is going to be done over here in the class, right? So Aloha has two variants. One is called the pure Aloha. The second one is called the slotted Aloha. We are going to cover both. Then we are going to go to the CSMA protocol. Then we will see like what is the disadvantage, what is the limitation of the CSMA protocol. Then we will go for the CSMA CD protocol and another one which is called the CSMA CA. Right. So the CSMA class of protocols, CSMA, CSMA CA, CSMA CD, all of these are very, very important because these are actually used in many of the modern day networks. So you need to understand this very carefully. But for the sake of completeness, we also need to understand Aloha and slotted Aloha. The reason is that these are like kind of the predecessors. These will help you to understand the basic concepts that are required for you to basically follow CSMA, CSMA, CA, CSMA, CD, right? So we talk about this random access. So this random access, basically these random access protocols, basically here, if you are talking about, just imagine that you have a shared medium, you have multiple stations, right? So random access protocols basically give privilege to all the stations to send their corresponding frames whenever they want to, randomly. So anybody randomly at any time, they can send their frame through the network, right? Through the shared medium. So if you think of it from another direction, here no station basically is given any kind of superiority over any other station for getting access to the medium for sending their frame. In other words, every station will have to, in certain way, content with each other to get access to the medium. And that is also the reason why these random access protocols are also called contention based protocols. So if a particular station has certain data, certain frames to be sent, then it uses a particular discipline which is enforced by a particular protocol, for example, Aloha, or for example, CSMA. So as dictated by that protocol, the station will be disciplined to get access to the medium. So it is going to decide whether it is going to start sending its frame or not. Mind you that in this kind of scenario, collision is something that you need to avoid at all costs, because none of the stations want their data to be lost due to collision, because of the reason that all of them they tried to send at the same time. So how can we enforce this kind of thing? So for this we will look into some of these different protocols. So before I do, let us take a quick, it is now 8:56. We will take a quick 1 minute bio break. Okay, so let us take a break and we will come back. So students, you also, if you want, you can take a quick break. Okay, so I hope that you all are back. So we need to understand how this is going to happen. Achha, by the way, so I hope that all of you have seen the question sets that have been circulated so far for our section. So I have given few questions which the TAs are going to post if they have not done already. So I have given you some practice questions for you to be prepared for, to help you prepare for your test, right? So it's not necessary that the questions in the exam are going to be from this question set, but the whole intention is that this question set, if you do independently, you will be better prepared for your exam, right? So let's go back, right? So let us talk about the first one, which is called the Aloha. So this Aloha class of protocols were designed. This is basically one of the earliest set of protocols that was designed and proposed in the 1970s, right? So in the 1970s for different stations to communicate over a LAN, right? And so the whole idea was to focus more on the wireless LAN, right? So on the wireless LAN, how these multiple stations they can basically get access to the medium. So in the University of Hawaii, basically this Aloha protocol, the earliest protocol, was proposed, and that is actually also the reason why you see this Aloha, right? So because it is University of Hawaii, I believe, right? So the name Aloha basically, it comes from these Hawaii Islands where these sort of names are quite common, right? So these sort of names or these sort of words are used by the people living over there. So let us try to understand how this Aloha works, right? So Aloha, as I said, can be classified into two types. One is the pure Aloha, the most primitive one, and the other one is called the slotted Aloha. So we are going to look at the pure Aloha first, and thereafter we are going to switch to the slotted Aloha. So this pure Aloha is basically this original Aloha, and it follows a very simple strategy that if any station has a frame to send, it will just send it. So whenever it has a frame to send, it is going to send it. So look at this particular scenario like this, right? So we have 4 stations in this particular example, which have different frames to be sent. And you see that if the x-axis is the time axis over here, then the different moments when the different frames were sent by each of these stations is also shown over here. Now, what Aloha does is that it says that station 1, if you want to send something, you send it whenever you want. Station 2, the same thing. Station 3. So everybody, so whenever they have any kind of frame to be sent, they send it. Now, this is number 1. Now, if you look at this particular figure, you see that this sort of mechanism, if you simply do it in a very naive way like this, then there are different moments where there are different windows, there are different moments when there are in the likelihood, there is a likelihood of collision, right? For example, in this scenario, you have during this particular duration of time, you have this probability of collision between frames 1.2 and 2.1, between 1.2 and 3.1, between 4.1 and 2.1, like this. So all these different frames, they can collide with one another during this span of time. So likewise, over here, have a look that 2.2, 4.2, they can also collide. So ultimately, what is going to happen is that if you have a scenario like this, only frame 1.1 and 3.2 are going to survive. All the rest of the other frames are going to collide with one another. So is this a good way to send the data? No. So you have to somehow handle this issue of collision. So let us say that there is some collision, right? So let us say that there is some collision, because collision is going to happen, right? So pure Aloha, basically, the whole idea is that it depends on uh, the use of something called the acknowledgements from the receiver. In other words, if the sender sends some frame, it depends on the receiver to send an acknowledgement back. Okay, so if the acknowledgement doesn't arrive within a certain duration of time, which is also called the timeout time. So if it doesn't arrive, the acknowledgement doesn't arrive at the sender end from the receiver within a certain duration of time, which is the timeout time, the station, the sender, basically will assume that there is a collision that has happened. So this collision could be with the acknowledgement, because of which the acknowledgement is damaged, or the collision has been with the original data, the frame that was sent, because of which the frame that was sent itself was damaged and was never received by the receiver. Okay, now this collision can happen, as we have seen, not just with the two devices, but it can happen with multiple devices trying to share at the same time. Now you see that the inevitable, the most logical way to handle collision is going to be that the either the frame has been damaged or the acknowledgement is damaged, because of which the sender, let us say one of the stations that you are seeing in front of you, one of these stations like station 1, station 2, etc., it doesn't receive the acknowledgement back. So it assumes that there is a collision that has taken place. So if there is a collision that has taken place, then these stations which had sent their frames, their natural tendency will be that they will try to resend the frames, right? And when they are going to resend the frames, they are going to resend the frames after the timeout period, right? Now you see that the pure Aloha, it says that after the timeout period, each station will wait for a certain duration of time before resending the frame. Why? Because if immediately after the timeout, if all the stations they send, then again there will be collision. There might be collision, right? If all the stations they try to send once again. So that is the reason, basically, pure Aloha says that you wait for a random duration of time before you try to resend your frame. So if it is random between the different stations, the wait time is random between the stations, then the chance of collision again is going to be minimized. Otherwise, if all the stations after the timeout, immediately thereafter, if they try to send, the chance of collision is going to be again as high as before. So you need to wait. Every station has to wait for a certain duration of time. This random duration of time, every station will be waiting. And because it is random, the chances of collision is going to be minimized. And this time that randomly, the random duration of time that every station waits, this time is called the back-off time. So every station on not receiving the acknowledgement for the frame that was sent out, after the timeout interval, every station is going to wait for the back-off duration of time, which is going to be different for every station. So every station's back-off time is going to be different. So how is this back-off time chosen? There are different ways in which the back-off time could be chosen. One of the most commonest ways is basically the algorithm, which is called the binary exponential backoff. BEB is the acronym for it, binary exponential backoff. So here in binary exponential backoff, the whole idea is that there will be a random number which will be chosen between the values 0 to 2 to the power k minus 1. 0 to 2 to the power k minus 1. What is k? K is basically the number of unsuccessful transmission attempts that were made by the station. K is the number of attempts that were made by the station unsuccessfully. So that is K. So the whole idea is that in binary exponential backoff, you first choose a random number between 0 and 2 to the power k minus 1, and you multiply that number with the maximum propagation time. Okay, so what is the maximum propagation time? Maximum propagation time is going to be between the two farthest stations, the time that the pulse is going to take to or the frame is going to take to travel between these two stations, which are farthest separated between each other. This is the maximum propagation time. Okay, so you multiply with that time. Okay, so that basically is going to ensure that to a large extent the chances of repeat collisions is going to be minimized. Now the question is 2 to the power k minus 1, where k is the number of attempted unsuccessful attempts, unsuccessful transmissions, number of unsuccessful transmission attempts, right? So how much is going to be the value of k, right? So if you increase k too much, that is also not going to be desirable. So the heuristic is that you use the value of k to be 15. This is what is suggested in this pure Aloha protocol. So finally, what you are going to have is this algorithm like this. So please pay attention over here. A station has a frame to send. So what initially, how much will be the value of k? As I said before, k is basically the number of unsuccessful attempts or number of attempts basically, right? So k equal to 0. Now then the frame is sent. Okay, you wait for 2 times TP. Okay, you wait for 2 times TP. Now the question is, why 2 times TP? You might ask, like, why it is 2 times TP? Basically, this is to ensure that the vulnerable period of vulnerable period of collision between the frames is avoided. The vulnerable period is avoided. So you wait for 2 times of the transmission, the maximum propagation time between the stations which are farthest separated. Then, whether the ACK has been received or not, a decision whether the ACK has been received. If the ACK is received, no problem, right? So that means the frame has been, it is assumed that the frame has been successfully delivered. If the ACK is not received, this is where basically all this complexity comes in. Then you increase the value of k to k plus 1. You increase the value of k to k plus 1. That means you are going for the next attempt, right? Then you check whether the maximum number of permitted attempts, which is basically 15, has been reached or not. If k is already greater than k max, then basically do nothing, you abort, you come out of this process, right? If it is less, you go for the second attempt. You choose the value of r. R means r is between, it's a random number between 0 and 2 to the power k minus 1. As I said before, that it's part of this binary exponential backoff algorithm. So you choose this value of r between 0 and 2 to the power k minus 1. Then you wait. So you choose that value and you multiply with TP, right? And that value that you get is going to be the backoff time. That value is going to be the backoff time. So you wait for that duration of time, and then only you try to send the frame. This is what the pure Aloha says. Okay, then only you try to send the frame. So this is how basically intelligently pure Aloha, it instead of sending on collision trying to send the frames once again, it suggests that you wait for a certain backoff duration of time and then you try to send the frame. This is what pure Aloha suggests. So I was talking about this vulnerable time, right? So you see that in pure Aloha, the vulnerable time is this much, which is basically 2 times TFR. What is TFR? TFR is the frame duration. Okay, so TFR, 2 times of frame duration, is going to be the vulnerable time. So how is it like this? Let us say that at a certain point of time t, frame B has to be sent. Okay, so you see that if you look at the t minus TFR instant, right, maybe there is station A which also sends a frame out, and if this is TFR, if this is the TFR duration, then at this boundary the chance of collision between the frames of A and B will be there. Likewise, if at t plus TFR moment of time another station C sends its frame, so what is going to happen? There will be collision between the B's frame and the C's frame. So you see that if you look at this entire scenario, this is this window from t minus TFR to t plus TFR, where there is a chance of collision between the different frames, and this is this window which is called the vulnerable time. So this vulnerable time, as you can see over here, it is TFR plus TFR, it is 2 TFR. Okay, or it is 2 TFR. Okay, so this is how you calculate the vulnerable window for the pure Aloha. So then comes the slotted Aloha. So slotted Aloha is better. So in slotted Aloha, the suggestion is that instead of trying to send at the same time, the stations will be disciplined this way. So the entire time duration is going to be slotted in this manner. So the time is divided into slots which are TFR, which are TFR, which is the time duration of a particular frame. So the frame duration, basically, as it is called. So this entire time duration is going to be slotted into durations TFR length, duration of time. So this is TFR, this is TFR, this is TFR, this is TFR, like that. And you make sure that every station follows this particular discipline, that they will be forced to send only at the beginning of the time slot. So station 1, it can send only at the beginning of this time slot. Station 2 can send only at the beginning of this time slot, and this process continues. So here, because of this discipline, basically you are ensuring that the vulnerable time is going to be TFR, right? So the vulnerable time is going to be TFR. So you see that slotted Aloha, it improves the performance by cutting down the vulnerable time to half of it. And why it is TFR? Why it is not 2 TFR? I think if you draw a similar kind of diagram like this, you will be able to realize that so the vulnerable time is cut down to half. Okay, so you see that so even if you are minimizing the scenario that we had seen before, so there is still a possibility of collision if two stations are trying to send at the same time. This actually you cannot avoid, and this is why this TFR length of duration will become the vulnerable time in slotted Aloha, right? So this slotted Aloha, the throughput of slotted Aloha can be calculated with this particular formula, the derivation of which is not in your syllabus. It goes through certain mathematical calculations, but it is sufficient for you to know that the throughput of slotted Aloha is G into e to the power minus G. Now, what is this G? This G has different values, right? So how we are going to calculate the G, I am going to talk about shortly through some example. Okay. So here you see, so in slotted Aloha, the throughput is going to be improved over pure Aloha, where the throughput was G into e to the power minus 2G. So obviously the throughput is going to be improved in slotted Aloha compared to what it was in the pure Aloha. Okay. Now a quick example. Let us say that we are talking about a pure Aloha network that transmits 200 bit frames on a shared channel of 200 kbps. So the question is that what is the requirement to make this frame collision free? So that means that you have to avoid the vulnerable time. So first, what you have to do, you have to calculate the vulnerable time. So is going to be how much? 2 TFR. Hello. Vulnerable time is going to be how much? 2 TFR. Am I audible? One of you please confirm.
Yes, sir.
Yes, sir.
TFR is basically, you can calculate this, that 200 bits it is given, right? 200 bits and 200 kbps channel. So TFR is going to be how much? 1 millisecond. So if TFR is 1 millisecond, the vulnerable time, because we are talking about pure Aloha, it is going to be 2 times of 1 millisecond, which is going to be 2 milliseconds, right? So this is how you calculate the vulnerable time, and the rest of the explanation follows. So let us move ahead. So let us look at a pure Aloha network that transmits 200 bit frames on a shared channel of 200 kbps. The question is that what is the throughput of the system if the stations, they produce 1000 frames per second, 500 frames per second, and 250 frames per second. So let us look at the scenario of 1000 frames per second. We are talking about frames which are 200 bit long, right? And the shared channel has this particular bit rate, so 200 kbps, and 1000 frames per second are sent by the stations. So you see that the frame transmission time, again, like applying the same kind of strategy like before, frame transmission time is going to be how much? 200 by 200 kbps, which is going to be 1 millisecond, right? Both these parameters are given, both these values are given, so you can easily compute the frame transmission time, right? So in 1 millisecond, we can, in other words, send 1000 frames, right? So if the frame transmission time is 1 millisecond, so basically, 1000 frames can be sent in 1 second, right? So what is the maximum capacity of the channel then? 1000 frames per second, right? So the first part is 1000 frames per second is going to be sent by the stations. So in such a case, the system is going to create 1000 frames per second or 1 frame per millisecond. Then basically G is going to be 1, right? How you are going to compute the G? G is basically the ratio of the number of frames the system is producing by the maximum capacity of the channel. The maximum capacity of the channel is how much? 1000. Number of frames the system is producing is 1000. So 1000 is the input frames from the channels. 1000 is also the maximum capacity of the channel as we have computed from here. So the value of G is going to be 1000 by 1000, which is going to be 1. So the value of S, the throughput, if you compute, you will get 0.135. So which is actually 13.5%. So 13.5% throughput means what? That if you are sending 1000 frames, out of these 1000 frames, only 135 frames are going to survive. If you are sending 1000 frames, only 135 frames are going to survive, right? So like this, you can calculate the value of G for 500 frames per second and the value of G for 250 frames per second. Exactly following the same approach that I said. So I have worked out for you over here. So please go through it and you'll be able to understand. Now, the next question is exactly the same like before, but instead of pure Aloha, it is now slotted Aloha. All the other parameters are the same. So if it is slotted Aloha, so the maximum capacity is same like before, but the value of the throughput is going to change. The value of G is going to be 1, number of frames being input per second divided by capacity of the channel, both of which we have computed. So if G is equal to 1, then the throughput is going to be 0.368, right, which is 36.8%, which means that if you are sending 1000 frames using slotted Aloha, 368 frames are going to survive. which is much higher compared to the throughput that we received, right? So in this particular case with pure Aloha, only 135 frames out of 1000 frames would survive, whereas in slotted Aloha, 368 frames would survive out of the 1000. So obviously we are improving the throughput. Likewise, please go through these ones for the different other values of T. Then, so let us come to any questions so far before we proceed to the pure CSMA, CSMA, pure CSMA. We have to do CSMA CD and CSMA CA. We have 3 tools to cover now. Any question? So, if there is no question, let us proceed further very quickly because we have about half an hour time with us. So, carrier sense multiple access basically says that if any station has any frame to send, it will first sense the carrier and then transmit. Okay, so it is basically the sense before transmit approach, or it is also called the listen before talk approach. Okay. Now, CSMA basically has the ability to further reduce the possibility of collision than slotted Aloha or pure Aloha, but it still cannot eliminate it, and we will see why it is so. So, in CSMA, the vulnerable time for this particular protocol is basically just the propagation time, which is TP, and which is actually equal to 2 TFR, which we will talk about later. Okay, so now why these are so, let us try to understand. So as I said, that carrier sense multiple access means that you sense the carrier, station senses the carrier, whether there is any transmission going on. If there is any transmission, then it will do something. If there is no transmission, it is going to send the bits. So let us try to look at this particular scenario. So in this scenario, what we see is that we have 4 stations A, B, C, and D. Let us say that station B starts at a particular time instant T1 to transmit the frame. So the first bit of the frame by B is going to be transmitted like this. So station A also gets it, and likewise it is going to be propagated all the way like this. So at a little later instant of time, let us say time T2, another station C, let us say that it sends its first bit of the frame that it intends to send. So the first bit of this one is sent like this, the first bit of C is sent like this. So you see these 2 bits, they collide out of these frames that are going to be the next bits that are going to be sent by each of these stations. So there will be the first bit is going to collide like this. Okay, so you see that this sort of approach has these problems because this is where you see that all these different places where the signals are going to exist, where it is going to collide, this is going to be quite evident by analyzing the diagram over here. Okay, so we need to take, we need to address it in a certain way. Okay. So, so you see that what is the vulnerable time? I told you that the vulnerable time for the CSMA is basically the maximum propagation time. Why the maximum propagation time? Because maximum propagation time is basically time the 2 farthest stations are going to time it takes a pulse to be sent, a frame to be sent from one of the farthest station to another end of another farthest station. The time that it takes, that's going to be the vulnerable time. So you see that when station A sends a particular frame, okay, B senses it. So if it senses, then it is not going to transmit. Likewise, C senses it. It is going to also refer its transmission. And E, it basically senses it for here. So this vulnerable time is going to be distribution of time, which is going to be the propagation time from for the frame to to the time that it takes for the frame that was sent by this station A to arrive at B. This becomes the vulnerable time. So the core, the heart of CSMA is that you need to have certain discipline, you need to ensure certain discipline if you find the channel to be busy or if it is idle. So for this, there are some persistence algorithms that have been proposed. Different networks basically use these different persistence algorithms. So these persistence algorithms basically dictate this particular station to do something, depending on the algorithm, to do something when the channel is busy or when the channel is idle. So the first one is called the one persistent method. So in this method, basically, after the station finds the line to be idle, look at this particular figure over here. So this is the busy period, and this is the point where the idle period is going to start. So when the station finds the line to be idle, it is busy, it starts to find that line is idle, then immediately it is going to send the frame. Immediately it is going to send the frame. I find the line to be idle, I send the frame. I send the frame with probability 1. That is why it is called one persistent method. Now, what is the problem? What is the problem with this kind of method? You see that if everybody does so, then there will be a very high chance of collision, because two or more stations will probably find the line to be idle at the same time, right? Although this is, although this is very naive and simple, and it has a very high rate of collision, primitive Ethernet protocol, the initial versions of Ethernet protocol that is used for the local area networks, Ethernet basically used this one persistent method. Okay. However, the later versions of Ethernet have evolved, but the primitive versions of Ethernet basically used this one persistent method. I hope that one persistent is clear to everyone, that whenever basically you sense that the channel is idle, you send it. Now everybody does it, so the chance of collision is going to be more. But it is very simple to implement. Now the non-persistent method is like this, that the sensing is done at different U sample, and you sense, the station senses, and whenever the channel is idle, it sends the data immediately, it sends the frame out immediately. If it is not idle, then what does it do? This is the beauty of the non-persistent method. If it is not idle, right? If the line is not idle, it waits a random duration of time and then senses the line. So if it is busy, it waits for a random duration of time. Random. So you see, initially it found it to be busy, then it waited for a random duration of time. It sensed once again, it still found it to be busy. It waits for another random duration of time, and then it tries to. So this is basically non-persistent. And the third one is called the persistent method, where you see it is like this. So you have these different time slots, and the station continuously senses. Okay. So the persistent method is used if the channel has time slots with a time duration equal to or greater than the maximum propagation time. Now it is not as simple as is shown over here. Okay. So persistent basically uses a little more complex algorithm. So it is like this, P persistent, and this is what you need to really try to understand. So with probability P, this is where this P is coming. With probability P, the station, it sends its frame, and with probability Q, which is 1 minus P, the station waits for the beginning of the next time slot, and then it tries to check the line again. Then if it finds the line to be idle, it goes to step 1. If the line is busy, it acts as though a collision has occurred and uses the backoff procedure. Okay, so this is basically how this P persistent method works. The corresponding flow diagrams are all given for you to go through. I'm not going to explain any further, but this is pretty simple. Whatever I have mentioned is given over here in the form of the flow diagrams, flow charts. Now, so CSMA is quite good in terms of avoiding collisions with the help of this mechanism of persistence algorithms, right? So CSMA is quite good, but CSMA, it can avoid collisions. It can minimize the number of collisions, but CSMA, it does not specify what a particular station is going to do if a collision has occurred. Okay, so for this, there is another algorithm which is called the CSMA CD, carrier sense multiple access with collision detection. Okay, this is called CSMA CD, carrier sense multiple access with collision detection. So in this method, basically, a station monitors the medium after it sends a frame to see if the transmission was successful. If it was successful, then nothing, it's fine, problem solved. If there was a collision, the frame is sent again. If there is a collision, the frame is going to be sent again. So you see that, look at this particular scenario, A, B, C, D, at time instant T1, the first bit of A, then, the first bit of the frame from A is going to be sent like this. Now, the first bit of frame C, let us say, is sent at time T2, which is greater than T1, at time T2, which is greater than T1. Now, this is going to be heard by the other stations also, like this. But the first bit of C and the first bit of A are going to collide like this, are going to collide over here. Right? So the collision is going to occur. Now this collision signal will be propagated all through, because it's a shared medium between A, B, C, and D. It is going to be propagated all through. Now that collision signal will be ultimately received at time T4 at A. So A's first bit, which has collided at time T2, will ultimately be heard by A at time T4. So if A sees that there was a collision, then it is going to abort. It is not going to, it knows that the frame is going to be, the one bit has, it has collided, means that, so it's going to abort the transmission. Now my question to you is that how is this collision going to be detected after all? Because this is the beauty of CSMA CD. The question is that how this collision is going to be detected in the first place. So this is the question. So please think about it and tell me. I'm going to be back in a couple of seconds. Okay, so who can tell how will the collision be detected by A? How does A know that actually there was a collision? Who can tell? Hmm? No one. So we'll try to address this particular issue, right? So how does A know that? I say, over here, all I have said is that A will detect collision, but how that collision is going to be detected? That is the question that I have asked. Okay, so let us hold on to this question and try to look a little further deep down. So this is basically the scenario of all the frame, all the bits of the frames being sent, right? And this is the point. These are the points where the collisions are going to be detected by A and by C in this panel, right? So CSMA CD, the algorithm is that you start with k equal to 0. Same, k basically represents the number of attempts. Apply one of the persistence methods like before, like in CSMA. Then whether there is collision or not. Okay, if there is collision, if there is no collision, basically you continue the process. If there is collision, then you find out whether the collision is detected or not. If it is detected, then what you do is that you send a jamming signal. Okay, increase k to k plus 1. Okay, then you find out increase k to k plus 1, and then what you do is you let me see over here. If the value of k has reached or not, if value of k has reached the maximum value 15 or not, right? So this is basically not appearing over here. This is the maximum number of attempts, right? I already told you that the value of k is going to be maximum 15, right? This is how it is hard set. So so if it has not reached 15, then you create a random number r, right? Like before, wait TB seconds, and then you apply one of these persistence algorithms once again. Okay, so this is how it is going to continue. Now, so I will not do this. Yeah. So the question that I asked, like so who can tell? I don't have the slide for it. I wish I could draw and explain to you. So let us just take this diagram. The question that I asked is how does A know that the collision is going to be detected? So the answer to this is because this is a shared medium between A, B, C, and D. The signal, the collision signal, like the other signals, are going to be propagated all through in the channel. So that means that every station is going to get a copy of the signal, the frame, right? So if the collision happens midway somewhere like this, so that collision signal is also going to be heard by the stations, all the other stations also. So what A is going to do is that it knows the frame that it had sent. It is going to compare that particular frame with the received frame, the corrupted one, where the signal is basically, it has altered the bit, and then it is going to do an XOR. If the result of the XOR is 0, that means the both the sent and the received frames are the same. If it is not 0, right? So obviously the received signal is different from the sent signal. Okay. So this is how basically it knows that whether there is a collision or not. So the one line answer is basically that it knows what was sent out. It does an XOR with what was received, and this is how it knows that whether there is a collision or not. So a few problems are given for you like before for you to work on, and their corresponding solutions are also given. But one important result in CSMA CD is that the minimum frame transmission time right? The minimum frame transmission time, which is the TFR, okay, is at least at least two times the propagation time. So the frame transmission time TFR must be at least two times the maximum propagation time. And why it is so? That also is quite, if you analyze a bit, that also is going to be not so difficult to understand. So TP once again is going to be how much? The maximum propagation time from A to D. Now let us say that just before it arrives at D, the propagation, the collision takes place, because A and D are farthest separated from each other, right? So let us say that a signal is sent from A, it propagates all the way. So this is going to be the TP, right? This is going to be the TP, maximum duration of time that it is going to take to go from A to D. D and A are farthest separated from each other. So then let us say that just before it arrives at D, there is a collision. So that collision signal again has to propagate all the way up to A for A to detect that there was a collision. So TP plus TP is going to be 2TP, and this is the theorem. The theorem says that the minimum frame size or the frame transmission time TFR must be greater than or equal to 2 times of the maximum propagation time TP. So this is an important result, and all of you please make sure that you do some problems like this with this particular result, right? So please work on this, and this actually I have taken from your book only, and in case of any doubt, please let us know. Now CSMA CD is good, but the main problem with CSMA CD is that in wireless channels you cannot use CSMA CD because collision detection is difficult. So you need to avoid collisions in wireless channels. Collision detection is difficult in wireless channels because you do not have any, any connected wire or anything like that. So if it is an open medium, so you need to avoid collisions, right? So in CSMA-CA, if the station finds the channel busy, it does not restart the timer of the contention window. It stops the timer and restarts it when the channel becomes high. So like this. This is why, pictorially it is shown over here. So this is your contention window. So it continuously senses. Then, it will wait for a certain duration of time, which is called the IFS, interframe sequence, I think, full form, right? So IFS duration of time, it is going to wait, and then it is going to content for getting access to the medium, and then finally it is going to send the frame. Right. So this is the whole idea of CSMA-CA, which is used for wireless channels. Now CSMA-CA uses a couple of mechanisms to basically to do the ensuring that the stations they are able to send their frames collision free. So the first thing is basically the use of interframe sequence. So this interframe sequence is basically the time duration that allows the front of the transmitted signal by the distant station to reach this particular station. So this IFS duration of time, basically even IFS comes in all different flavors, DIFS, then many other, DIFS, SIFS, short interframe sequence, etc., DCF interframe sequence, and so on. So different flavors of it are all available. So IFS duration of time is basically the time that the station is going to wait before it is going to attempt to send the frame. Now there is another one which is the contention window, and this contention window is basically the time duration which is divided into multiple slots. Okay, so a station that is ready to send basically chooses one of these random slots as its wait time, and the number of slots in the window basically changes according to this binary exponential backup strategy that I already mentioned before. So like this, basically this contention window, interframe sequence, and another one which is the acknowledgement, which is basically the positive acknowledgement from the receiver to the sender, acknowledging that the frame is received successfully. These three things, along with another thing which is called the RTS sequence, these are basically used by CSMA to basically help the stations to talk to each other collision free, right? Not collision free, I mean 100% collision free is difficult, but it tries to avoid collisions. So let us look at the flow diagram of CSMA. So like before, k equal to 0, but over here, if the channel is free, before doing anything else, it first lets the channel wait for this IFS duration of time. And now the question that you will ask, like, how much is the IFS duration of time? So it actually depends on the wireless network that you are talking about. So IEEE 802.11a has certain, certain IFS duration. Then B has certain other IFS duration and so on. So it's all dependent on the particular wireless network that we are talking about. Not only so, but also the different variants of this IFS, like TIFS, SIFS, these are also like different and so on. So let us just talk about only one IFS, which is like this interface sequence, and then it is going to interface space. Right? Basically, it is not interface sequence, but interface space. So it waits for IFS, then it chooses a random number r between 0 and 2 to the power k minus 1, and uses the RF slot. Right. So this is basically, this r value is computed from 0 to 2 to the power k minus 1, and then that r value is used as the slot to be chosen in that context. And in that slot, first you send a request to send frame, RTS frame. So RTS frame basically is sent by the sender to the receiver, whether the receiver is ready to receive the frame or not, right? So only after the receiver says that it is clear to send, then only, so the receiver has to send a CTS, right? For every RTS, the receiver has to send a CTS back. Then only basically this frame from the sender is going to be sent, after waiting for another IFS duration of time, which is basically this IFS, this IFS, which is basically the SIFS, right? Short IFS. This is called short IFS. So this IFS was BIFS, this IFS is SIFS. So for IFS, SIFS duration of time, it will wait, and then it is going to send the frame. And then, so it sets the timer, so then, it sets the timer, and whether the acknowledgement is received. If the acknowledgement is received, no problem, but if the acknowledgement is not received, you increment the value of k to k plus 1. If the value of k is not is below the limit, which is 15, you calculate TB and you wait for those TB seconds, right? Like before, like in CSMA. Right? So what are the mechanisms that are introduced in CSMA over CSMA? One is IFS, second is acknowledgement, third is contention window, fourth is RTS CTS. So with all these mechanisms, basically, you are going to use the CSMA. Now the question that you might ask is, if CSMA can work very well, why don't you use only one, which is CSMA in wired network as well? In wired network, typically we use the CSMA and in wireless we use the CA. The question is that why can't we use CSMA in both, right? So the answer is that CSMA or rather other way put, CSMA is basically more efficient compared to CSMA. CSMA is more efficient compared to CSMA. Because we could not use CD mechanism in wireless network, we had to go for this roundabout way of RTS, CTS, and the other things that I mentioned to do this particular thing. So now in wireless terminals, basically in wireless networks, there are two things which are very popular. Three problems actually. One is called the hidden terminal problem. The other one is called the exposed terminal problem. In the hidden terminal problem, basically, if a particular station, so let us say that we have two stations, right? Three stations, A, B, and C. We have three stations, A, B, and C. Now, if station A transmits something and then if station C also transmits something, A and C are basically hidden from each other, right? Because these are hidden from each other, as such they cannot hear the transmissions of each other, and because of which basically there is going to be a collision at B's end, right? So this is called the hidden terminal problem. So this hidden terminal problem, and another problem which is called the exposed terminal problem. So in order to solve these problems, basically this RTS CTS based mechanism can help. So in exposed terminal problem, you see you have something like this, that station A, B, C, and D like this. But let us say that B is transmitting to A, C is transmitting to D, but B and C, they are basically in the range of each other, right? So because of this, basically, so one will be basically exposed to the transmission of the other, and so they are even if they do not want to send the frames to that particular station which is exposed, but that exposed station also cannot transmit because it thinks that there is some transmission that is going on, and that basically leads to underutilization of the channel, right? So hidden terminal and the exposed terminal problems are basically typical problems that occur in wireless networks. So whatever I mentioned is explained over here. So the use of RTS CTS, basically, first before you try to send the frame, you send a RTS frame, and then you get a clear signal CTS from the receiver station, and only after that the data frames are going to be sent. So this is basically how it works in the walkie-talkies also. So that mechanism is implemented in wireless networks with the help of RTS CTS frames. Another problem that is very common in wireless networks is basically the near and the far terminal problems. So here basically we have A and B, which are both sending with the same transmission power. A and B are sending with the same transmission power. As the signal strength basically decreases proportionally to the square of the distance. This is a well-known thing in wireless network, that the signal strength basically decreases inversely to the square of the distance. This signal basically counts out a signal, right? And as a result, C cannot receive A's transmission. C cannot receive A's transmission, right? Because B comes in between, and the signal strength of the signal that is sent by A is going to be down by B's signal, right? So C cannot. So far terminal and near terminal problems are some practical problems that happen with wireless networks. So the other type of mechanism, which is called the controlled access mechanism, here basically, so there are three types. One is called the reservation, the other one is called polling, and the third is called the token passing. Now, reservation, basically, in reservation mechanism, before a particular station needs to send a particular frame, it's going to reserve the channel before actually trying to send the data, right? So it has to reserve for a certain duration of time, right? And so this is basically how these reservation mechanisms work. And the polling mechanisms basically work in a similar way as the roll call based mechanisms work in the class, right? So there is a teacher who acts as a controller. So the controller basically sends a message to each of the nodes in turn, and so there is a leader and there is a follower kind of mechanism, and this is how basically this polling is done by the controller, and the secondary stations, that means the other stations, are going to basically respond to the polls depending on the request that is sent from this controller, the primary station, right? So this is basically the polling mechanism. So reservation mechanism, polling mechanism, these are mechanisms that are part of this method, right? So this reservation method. And the third one also I have missed out, but this is something that I had explained in one of the introductory classes, which is called the token passing mechanism. So basically, so you have kind of a ring kind of network, and a token is sent from one of the stations, right? So the tokens are basically, the token basically passes around the ring from station to station. So whichever station has some frame to send, it gets hold of that particular token, and it puts the data into it, and then it sends across. And the station which has the destination address marked in the token, it's going to get the frame, and it will keep the data and again pass the token forward, right? So this is basically how this token passing mechanism also works. But it is not very common nowadays, but still it is in the interest of completeness. I just wanted to let you know that this sort of mechanism is also So the token basically, the ring doesn't have to be a physical ring, right? So physically, it's not like that they have to be connected with in this particular fashion. But logically, so with the help of successor predecessor kind of mechanism, which all these nodes they know, like so which one is the successor, which one is the predecessor. So logically, basically, you can form these rings in this manner. So you have the physical ring, you have the dual ring, you have the bus ring, you have the star ring. So all of these basically through a combination of the successor and predecessor pairs, you can like which session basically goes where. So in another 2 minutes, I'm going to finish, right? And that will complete our chapter over here. The last type of methods is called the channelization-based methods, and this is what yesterday and today in the beginning we were also talking about fundamentally. So frequency division multiplexing, time division multiplexing, and code division multiplexing are used in order to come up with these multiple access mechanisms, right? So multiple access through this frequency division multiplexing, time division multiplexing, and code division multiplexing are going to be used in order to in order to discipline the stations, like when they are going to transmit what, right? So in FDMA, frequency division multiplexing, as you can see that the different stations, they have different different frequencies in which they can transmit, right? So station A over here, station B in this frequency range, station 4, sorry. So station 1 in this frequency range, station 2 in this frequency range, station 4 in this frequency range, and station 3 in this frequency. So they know, in which frequencies they are going to communicate. So this FDMA basically is an extension of this FDM concept in order to provide multiple access to these different stations, right, in the different frequency ranges. PDMA likewise gives predefined time slots to the different stations, right? So these time slots are shown over here, color coded. So the PDMA basically gives the predefined time slots to the different stations. And CDMA, which we have not covered and we do not cover in detail, uses the code division multiplexing, which I mentioned today. That code division multiplexing uses certain things called codes. And these codes are basically cheat codes, right? So this is basically, so every station which wants to send send the frame will basically have access to a particular code, and using that code only it will be able to send the frames. So CDMA basically uses that kind of mechanism. So with this, basically, we covered, we complete these multiple access protocols. Once again, I just wanted to remind all of you that so till this particular part, the test that you are going to have next week, it's going to be there your syllabus. So thank you so much. I'm very sorry that couple of minutes we are a little delayed, and I hope that all of you please go through all the materials and you try to be